All right, welcome back. I hope you're having an awesome time so far. Our next speaker is Mahasa Zahirnia. She's the Chief Engineer and Artificial Intelligence Lead at Northrop Grumman. Please join me in welcoming her to our virtual stage.
Good morning, everyone. My name is Mahasa Zahirnia, and today we'll be discussing the process of using artificial intelligence within the cybersecurity environment. The agenda of what we will be discussing, we'll discuss the purpose, overarching concepts, some design parameters that allows us to design out the cybersecurity agent within our product portfolio, the pattern receptors, and the agent's design requirements. Today, the cyber threat and the cybersecurity incidents are silent enemies, and they're overtaking multiple organizations with massive amount of breaches. This industry is over-consuming with bad actors, and we really are not understanding the root cause analysis of the attacks that are imposed onto the product. The product owners are very codependent on the network infrastructure and the OS environment to do the detection for them. Once the OS and the firewalls are breached, as they often are, the system is left helpless without any support mechanism to protect itself. So what my design wants to do or understands to do is to really put the cyber intelligence within the product, and so that the product can handle and control the environment and control the issues. So the overarching concepts is the next set of slides that I'll be discussing. What we like to do when we design out a system is create a block diagram that allows us to take the cybersecurity agent into pieces and where the tasking is. So what the agent does is, in the first stage, it really does start looking at the interfaces. And these are human-to-human interfaces. This is system-to-system interfaces. This is CSCI to CSCI interfaces. The agent is monitoring these inputs and outputs so that it can kind of like protect itself. Then it does the surveillance and looks at the layout of the product and all the tasking that it has to do based on those inputs, and does this matching. There's this matchmaker agent that I have developed, and not only it looks at the IP addresses and the IDs and the passwords, but it looks at biometric behaviors and kind of like analysis of the human activity within the product, so it can portfolio the user and the type of user that are inside our product. Then at the bottom stage, it really is the workhorse of the agent, where this agent understands the footprint of the application that is being utilized by this external body, whether it's a system, whether it's a human, and so on, and really starts detecting the normal and abnormal behaviors. It has a malware agent and understands the layer and layout of the type of viruses that are possible. It creates the attack tree. It builds a sort of an AI builder, agent builder, that it uses a certain set of state diagrams that I will be explaining later on. And it can create a new state diagram by self-evolving code that is part of the solution of this cybersecurity agent. And obviously, when it does all this collection of information and understand the trend and understand the actual virus, the zero-day virus, it provides information, solution, and activation of protection and countermeasures. A lot of this area is really very dependent on your customer and how you want the agent to be engrossed in this specific area is very customer driven. So what we want to build is for the agent, we want to build a learning, massive amount of learning with that is engulfed in interface and interaction within a system and with the human interfaces. It has to understand the natural environment, and it has to understand that layer of information. We don't necessarily have to explicitly program every step that he's learning, but we are giving him some reasoning with interaction with us and the environment. One of the most important things we do when we try to understand an unknown, we have to understand the viruses, the unknown virus, the zero-day virus, is that we have to understand the specification of this virus, this thing that has came into our application. We have to understand the behavior of the virus. This I will later on define it as pattern receptors that I have designed out. We have to understand the interaction between the human, the system, and CSCI, such that we minimize the false positives. This is identified by the product mission and the human applications of the product mission. Then we also have to, this agent shall also do cataloging, categorizing the zero-day viruses so that we understand what is the true cause and effect of this virus. The agent not only does a diagnosis, but it also provides recommendations and course of action. And more of cognitive approach, we like to use the 80-20% rule, where 80% of the data that is consuming, it understands it and identifies it, and the other 20% that are unstructured, it formulates an objective and delivers those objectives to the customers. And this agent is really the health monitor of the product inside the product, and it will take proactive measurements as needed. This data flow diagram that I have outlined here is very similar to a detective that is coming into a crime scene. So we get the information that we have a wrong file, wrong data, wrong time that has just came into our agent. What the agent does is detect and verify that this is a malicious behavior. It takes a preservation of the data. It takes a snapshot of what is going on. And then it starts explaining the data. It builds the attack tree. It builds the 4 out of 5 matches for a cause and effect. It creates the boundaries, and it starts doing the symptoms analysis. It's exactly the same thing as a detective does. This is the steps that we need to take to sort of understand the virus so that we can do accurate evaluation. We can identify the mission and the vision of the threat. You see, when we get a virus in, we have to understand what the portfolio of the work that the virus is doing. And we have multiple avenues of trying to understand and put that picture together. This agent is building that picture for you instantaneously. And obviously, after it identifies and understands what this tasking of this virus is, it can perform the CPR, it can start doing the countermeasures. The overarching concepts is because we're interfacing, we're on a network, obviously. So we have a lot of resources out there that's kind of pulling data for us, for the product owner, for the cybersecurity within the product. So we have to pull that information in and collect that and become a cohesive dance between the product owner and its environment. So we get all the Splunk and all the network management tool in. We also have to do massive amount of data collection and noise reduction for our product to be able to work seamlessly. A lot of these areas have already been understood and well defined, so I don't need to explain to you the details of those designs. We do noise polishing, we do remove irrelevant data, we cluster like objects, and we do association learning. I sort of started diving into this design when I was a Splunk manager and I was doing exact same scenario, but I was doing it too late. You know, or if the product has already been breached, Splunk is already too late. So I decided and understood that this has to be done instantaneously inside the product. We're going to also make sure that this agent does the access management, does the language processing, facial recognition. These are key elements of biometric measurements that we have to be able to ingest. We can no longer depend on the IP addresses and passwords and even security keys for us to really understand the situation. We have to do the language processing, facial recognition. We also have to, it's very critical for us to really mimic the human interfaces by when this guy clocks in, what files does he use, what's the speed of keys that he types into the keyboard. These are the parameters, key behavioral parameters that identifies Mahasa as Mahasa. And if those don't exist, we can mimic that very easily and bypass those type of problems. It has to do predictive analysis. It has to understand the traffic of information and the traffic of data that is being transferred and how the human is interfacing with that. And we have to be able to predict. We know that Mahasa works 5 days a week. That prediction is there. We know these are her hours. This is where she works at. So anything beyond that will give us a clue of an issue. It has to learn adversarial training. We have to employ the attack calculations onto the agent so that the agent learns from those attacks. Just like a human, that we expect to have cyber trainings and do counter attack measurements and have those learning curves, our agent has to do the exact same thing. Additional overarching concepts. We want to do the authority, certification authority within the product. I know there's a lot of hesitation there. I understand it. Why? Because it's a huge responsibility. But if there are breached within, we have multiple agents. They all have their own security certification. One of them can be attacked. And if that is attacked, we can certainly shut down that comms between when that agent is performing that task. But there are other pieces of the product that agent has already stepped on, and he can continue to do other tasking. So we have to shut him down, not only shut down the comms between the agent and the CSCI. So we have to close him down by locking him out if our own agent is under attack. We have to do the matchmakers before committing to information transfer. We have to identify the impersonation of the agent. And I like to use a triangle key parameters where I have one agent doing the actual tasking of monitoring, another agent is managing the first agent, and the third agent is doing an overall approach. Now, what I like to do when I design this out is that triangle shifts, right? I have one guy doing the work, the other two are monitoring him or and each other, but I like to shift that work around so I no longer have single point of failure, and the tasking gets rotated instantly, autonomously, and nobody really knows who is the boss and who is leading and who is passively monitoring. We want to do 0-day attacks, best out of 5 symptoms. We have to do the behavior analysis, and we have to have accountability, such that I just explained, a multi-agent system. Supervised learning is the bread and butter of our agent. We have over 2 billion threads. We know that threads are built on threads. We know there's distinguishing characteristics. So once we give that baseline to the agent, we allow him to be educated of the process. We already give him some understanding, some compassion, and not let him be blind every time a virus comes into the environment. So while we give him these threats, we also have to give him deep network training, understand the normal behavior, or even characterize the normal behavior for him. We have to do the adversary training as is important. And adversary training is not a static environment. It's a dynamic environment. We look at, we have the agent to search the existing chatters, the trends that are out there, and build hypotheses based on those threats that it sees, and comes back with threat actors. This is a proactive agent that's out there, that's collecting data from existing information that is available, and the threat analysis can be created instantly by this agent. We do the spam training and the unlabeled attack detection that comes placed hand in hand with adversary training as we're learning, doing those learning curves with current existing information that's available to the agent. Unsupervised learning for the agent, I like to use the Markov model equation. That gives me a lot of compassion and a lot of understanding of what the agent can do, his tasking. As you can see with the small diagram on the side, we build a state diagram that this agent is getting rewarded as it goes from each task to another task. I will give you more detailed explanation, bigger state diagram for the design that I'm implementing, but I have a small one here sort of to start giving you the vision. So this equation, what it drives, is looking at multiple states. The activity of the agent starts at state 1 and finishes the task at state 10. These tasks that he does at each one of these stages are really identifying the threat. As he executes each one of these stages, he can move to the next stage and reward. So every time he finishes a task at a state, we reward him with knowledge information, and we're allowing him to capture that data in and says, okay, this is the task that I did. This is the information that I collected. If I complete this task, then I'm rewarded with this information. We also give him probability. We allow him to make decision based on present and the future prediction of the reward system that he's going to get. So the agent tasking with the state diagrams is to really build these objectives. How close is the signature pattern to the known patterns? When can we start flagging the 5 out of 7 elements? What does the various trends look like based on these activities that we just completed? So not only he has to finish the task of identifying the virus, he also has to do additional knowledge and breadth into what he just finished by completing these tasks. Pattern receptors for supervised, unsupervised learning. I understood the pattern receptors within the human body, how our human kind of looks at the virus and starts doing different tasking. These are the receptors that are utilized by the agent to collect the information to start doing the state diagram that I just explained. So machine learning and pattern recognition go synonymous. They're synonymous together. This is a teaching tool that those detectors go out there and try to understand, right? So our receptors, I have divided them into 4 receptors here. You could have 10. I just started the conversation, so you guys can go out there and design this out as needed. So we have 2 like receptors. These are the guys that already know the malicious behavior based on the existing malicious behavior that we already have identified with those 2 million viruses that we have ingested. Next, we're going to look at the deep learning and understand what the virus is. The first thing we do is we look at the structure of the virus. What is the unique structure of this virus? So for example, if we look at a picture of a building, we look at specific structure and we say, okay, this is the way the structure of this thing is. That's exactly the same thing. We want to understand the specific figures. What is the features that makes this virus unique? And once we understand that, we can understand the behavior and catalog and categorize the attack. And we have to give specific characters, right? There's a specific key ingredient of the attack that makes it, that identifies the attack itself. Like, for example, invalid IP address. That's very simple. It's a very key ingredient. It said this guy is coming in with an invalid IP address, and therefore I have to go to the next step. At least it gives me the starting point, right? And so this is basically formulating the attack scenario, shall we say. These receptors also do specific things, right? We want them to do action. We want them to take action, right? We want to take interface with the destruction and stop this destruction. We want to do corrective action, do the restoring of the damage and restoring the environment. We want to engulf the virus, encapsulate the virus. And we also want to create policies. Once we understand the zero-day attack, we want to document these results. And when I mean documentation, not a 5-page dissertation sent to your management, really creating policies for the agent. These new policies allows the agent to go add new values, start new routes, building new codes based on those new routes automatically, and have variety of flavors of policies that can be utilized on the cluster of viruses that we just identified. The agent design, some of the high level design, when we get into, once we do start building those requirements, as I just explained earlier, now we're doing sort of laying out the design itself. Again, we're going through the biometric information that we have to understand and explore. We have to do edge computing. We have to utilize supervised and unsupervised algorithm. And we have to get this information into the agent as readily as possible. So now we start doing use cases, right? For you to identify and be able to develop that for the developer, you have to build these kind of diagrams for them so that they understand the IO interfaces. This is a very simple diagram, but I think it meets the purpose. This is when you're first talking to the human or the profession trying to access your product, and you do certain authentication authorization with him. And this is massive amount of information because we have done the behavior analysis, we have taken into biometrics. Again, it's not as simple as password and usernames. Those are easily bypassed. Once we are into the system, we have to know what CSCI and what CSI, what are they communicating, and what is the cyber intelligence within that environment. For example, keep private is one of those cyber intelligence that we have ingested into the application. A lot of people say, well, we already done that, Mahasa, but what's important is that this is not static. It's an AI-based design, and it's self-evolving and self-healing based on the data feed and the environment that it has and its own success rate. And I will give you an example of the state diagram for this keep private, so you can see what I'm trying to say. So next up, we're adding more resources, external bodies, and adding more and more, shall we say, steps to our cybersecurity intelligence. This is Markov decision process for keep private. So for example, we start with the S1 state 1 diagram. We have a cause of an issue. A file was opened at the wrong time with the wrong date and a wrong user. And we allow the agent to make decisions. He can go one way or another depending on the route that he wants to take, and depending on what's the most likely in this scenario, we're giving him 50% chance to go one way or another, because our application can be web-based or can be the application that you don't have to use a web base. So this probability of going one way or another has to become total of 1. That's critical. And the reward system is the lowest reward system because you're at state 1. Once he's able to identify that and move to the next step, again, we're giving him through the same processes and which way we want him to go. In this scenario, the probability of is 0.9. We actually want him to go through the web interface and understand that if this wrong file was utilized through the web interface issues that it sees. So if you go through each one of the steps, what's important and what is different than a static step diagram is that we're giving it probabilities. We're allowing it to make decision based on environment. We're allowing it to reverse course when it needs it. We're giving it the reward. We're allowing it to collect that information. We're also forcing it down the path, the journey that it needs to go to continue and finish his task, right? We want him to get to highest reward system that is allocated at the finishing task. Now, R is 0 here is because this is a resting period. We don't need him to continue any further, so we give him a 0 for this reward system, and this has the highest reward. Security agent, this is a really description of what we just explained, the reward system and the activity that he needs to take for each one of these steps. What's important is that we build this AI agent, employ the cybersecurity system team that have their feet in both areas, in AI and in cyber. The source code generation is a really easy artifact that we can do. We can employ it to do the stopgap for a zero-day attack. Our designs have to take the risk mitigation out of the game by building attacks and counterattacks so that we test ourselves out. What are the drawbacks? The drawbacks is obviously this is massive amount of work. There's a lot of data that has to be collected and consumed. So for us to have a stable environment, hackers can AI proof us. They can countermeasure us with their own AI environment. I always people ask me this: can AI replace humans? No. There's a certain amount of cognitive knowledge, a sort of workhorse that the AI can do that and can do it 1,000 times faster than us. But we really can weigh out the customer comfort as those activities, the final activities has to be done. So we have to, the AI agent is our workhorse, but we're the person who's making the final decision. It's not cheap. This is a work that needs to be done. But we understand the dilemma of small size products that really don't want to invest in them. So our recommendation is to build those AI-driven products and be able to customize it. So we have already certain level of information, the threads that already been ingested, build those in and start customizing from there. I think that's it. That's the end of my presentation.
Awesome. Thank you so much, Mahasa. If you could just stop sharing your screen so that we can bid the audience adieu. Awesome. Well, thank you so much. We really enjoyed your presentation and we appreciate you sharing your insights with us.
Thank you so much.
Awesome. If you're looking for your next session, you can go ahead and check out your agenda or take some time to connect with your peers with virtual networking. Thanks so much and we'll see you around.
Thank you. Good day.